Hello, you're welcome to the final video in this playlist on derivatives or differential calculus. And we're going to be talking about curve sketching, where we'll examine the various steps that are involved in sketching a curve properly. So, before taking a question, I'm going to outline the steps that are involved in sketching a curve. So, the first step is to find the domain and possibly the range of the function. So in order to find the domain of a function, we're examining all the points at which the function is defined. So for all values where the function is defined, that is values of the independent variable, all values of the independent variable where the function is defined, they constitute the domain of the function. While the range of the function is simply just talking about the span of the values of the function itself. How large does it span or how little does it span? That's what the range of the function refers to. And to get the range of a function, for functions that can be easily, okay, say for instance, we have y is equal to 2x minus 2. For functions where we can make x the subject of the formula, then you can use that. Then the function you get after making x the subject of the formula, you can find the domain of that function. And that's just going to give you all the possible values of y, that is the range of the original function. So, or you can just find the inverse of that function. So by finding the inverse of the original function and finding the domain of that inverse function, then you can get the range of the function. That's how we approach that. Then the next step after finding that is to get the intercepts on the x and y axis. So we've probably come across this when we're treating straight line concepts in our various studies. But to find the intercepts on the x-axis, what we're going to do is to set y to be equal to 0. That is, we are looking for the point at which the curve cuts the x-axis, and at the x-axis, y is equal to 0. Likewise, to find the intercept on the y-axis, we are going to set x to be equal to 0 so we can obtain the point at which the curve cuts the y-axis. And at that point, if the point lies on the y-axis, then it means x is equal to 0. And that's how we obtain the intercepts. Next thing is to obtain the symmetry about the x-axis and possibly the y-axis. So before I continue the explanation on this, to also find the range of the function, one can evaluate the absolute minima and the absolute maxima of the function. So that's going to give us the highest possible value that a function can be in the absolute maxima. Then for the absolute minima, it tells us the lowest value that the function has. So by knowing the absolute maxima and the absolute minima, we can know the range of a function in case the function cannot be, or in case the inverse of the function cannot be found. So as regards the symmetry about the x-axis, what we are trying to do is to test for the evenness or oddness of the function. So if we have a function given to us, if we test for the evenness or the oddness of a function, if we realize that the function is even, then it means the f of x is equal to f of minus x. And that means it's going to be symmetrical about the x-axis. But if the function is odd, it is not going to be symmetrical about the x-axis. The same would apply to the y-axis, provided that you can find or you can make x the subject of the formula, then substitute minus y. If by substituting minus y you get the same value as you get by leaving just y in the function that you got after substituting or making x the subject of the formula, then it means that it is symmetrical about the y-axis. But most times what really matters is the symmetry about the x-axis to give you an idea of what the curve will look like. After getting or evaluating the symmetry, the next thing to look into is the stationary points on the curves. We've come across stationary points in the previous videos. Likewise, the evenness and oddness, that was the first video in the playlist. So we can check that out for under functions. For the stationary points on the curve, we evaluate the first derivative of the function and we equate it to zero. The values of the independent variable that we get there is what is going to be are those values that will be our stationary points on the curve. Then after evaluating the stationary point on the curve, we now determine if they are maximum points, or let's say maxima, minima, or points of inflection. So after doing that, to get if it's maximum, minimum, or points of inflection, we perform the second derivative sign test. So we find the second derivative of the function, then we substitute the relevant values and check if it's greater than zero in the case of minimum values, if it's less than zero for maximum values, and if it's equal to zero for points of inflection. The last thing is to evaluate the behavior of the curve around the intercepts. Sorry, around the intercept on the x-axis. We are doing this to have an idea of where the function is increasing or where it's decreasing, where it is concave upwards, where it is concave downwards. So these are the reasons why we examine the behavior of the curve around the intercepts. So let's take an example to see how this works. Sketch the curve y is equal to x multiplied by x minus 3 multiplied by x plus 2. So to start with, we are going to be finding the domain of the function. So it is evident that this is a polynomial, and for every value of x, the function is defined. Hence, the domain of the function is minus infinity to infinity. And this is because the function is defined for all x. After finding the domain, we can check to see the limits of the function as it tends towards infinity. Maybe that can give us an idea of the range. As x tends towards infinity, for this function x multiplied by x minus 3 multiplied by x plus 2, we can see that this is going to give us three different values: infinity multiplied by infinity multiplied by infinity. And from our knowledge of limits, as treated before, we know that this becomes infinity. And also we know that the limit of x multiplied by x minus 3 multiplied by x plus 2, as x tends towards negative infinity, is going to be equal to negative infinity multiplied by negative infinity multiplied by negative infinity. That's just bound to be a very large value of infinity. So that gives us negative infinity. So it shows that as x tends towards positive infinity, the value of x gets progressively larger, and as x tends towards negative infinity, it gets smaller, but it increases in magnitude. So that means it's safe to say that we know the absolute maxima and the absolute minima Thus, the range is going to be minus infinity to infinity. So we found the domain and we've also found the range of the function. So the next thing we want to try to do is to obtain the intercepts on both axes. So to obtain the intercepts on both axes, for the x-axis, we'll set y to be equal to 0. So setting y is equal to 0, we have that x multiplied by x minus 3 multiplied by x plus 2 will be equal to 0. This means that x is equal to 0, minus 2, or 3. So it means that the x-intercepts are as follows, as minus 2, comma 0, 0, comma 0, and 3, comma 0. These are the x-intercepts. So for the y-axis, if you set x is equal to 0, then you have y to be equal to 0 multiplied by 0 minus 3 multiplied by 0 plus 2. So for the y-axis, we have this to be equal to 0. So it means the y-intercept will be equal to 0, comma 0. And we've gotten the intercept on both axes. Next thing we want to examine is the symmetry. So to examine the symmetry, which is the third point, I've said that we are going to test for the evenness or oddness of the function. So if f of x is equal to x multiplied by x minus 3 multiplied by x plus 2, that means that f of minus x is equal to minus x multiplied by minus x minus 3 multiplied by minus x plus 2. So this is not the same thing as f of x, and it's even not the same thing as minus f of x. So therefore, f of x is neither even nor odd, and it is not symmetric about the x-axis. So we are not expecting any form of symmetry along the x-axis. So the next point is to find our stationary points. To find the stationary points, we'll set our first derivative of the function to be equal to 0. So f of x is equal to x multiplied by x minus 3 multiplied by x plus 2. And this is equal to x raised to the power of 3 minus x raised to the power of 2 minus 6x. So we can evaluate the first derivative of the function. F prime x now is equal to 3x squared minus 2x minus 6. So if f prime x is equal to 0, we have 3x squared minus 2x minus 6 to be equal to 0. So by solving it using the quadratic formula, we have that x is equal to 2 plus or minus square root of 4 plus 72 divided by 6. So this is going to give us 1.79 or minus 1.12. So let's find the values. At x is equal to 1.79, if you substitute this into the function, you have that y will be equal to 1.79 multiplied by 1.79 minus 3 multiplied by 1.79 plus 2 and you would have y to be equal to minus 8.21 approximately. Then at x is equal to minus 1.12, we have that y is also equal to 8.68. So we know the values of the stationary points now. The next thing is we want to perform the second derivative test, that is f prime prime of x now becomes 6x minus 2. So since we know that f prime prime of x is equal to 6x minus 2, then at x is equal to 1.79, we have that f prime prime of x is equal to 6 multiplied by 1.79 minus 2. So this is going to give us 8.74, which is greater than 0. Therefore, x is equal to 1.79 is a minimum point. So when x is equal to 1.12, you have that f prime prime of x is equal to, minus 1.12. F prime prime of x is equal to 6 multiplied by minus 1.12 minus 2. So this is going to give minus 8.72, which is less than 0. And this shows that x is equal to minus 1.12 is a maximum point. So since we've established the stationary points, the last thing we need to do is check the behavior of the curve at or around the intercepts. So we examine the three intercepts: x is equal to minus 2, x is equal to 0, and x is equal to 3. Then we check the behavior of the curve there to have an idea of how the function is going to behave. The next step is to now check the behavior of the curve. So we should recall that the intercepts are at minus 2, 0, 0, 0, and 3, 0. So if you set up intervals within those 3 points, if you have minus 2 here, you have 0 here, and you have 3 here, it means you are examining what happens to the left of minus 2. You're examining what happens between minus 2 and 0. You're also checking for what happens between 0 and 3. Then you're examining what happens to the right of 3. So writing that in inequality form, we're having x is less than minus 2, minus 2 less than x less than 0, 0 less than x less than 3, then x is greater than 3. So those are the possible intervals that we can have. And we can now prepare a table to look at how the function behaves around these intervals. So now we're just going to be looking at the signs for each of these functions. So we have x, we have x minus 3, and we have x plus 2. After which you now have the original function when you multiply the three signs together. So when x is less than minus 2, we know that the sign of x is negative. When x is between minus 2 and 0, the sign of x is negative. When x is between 0 and 3, the sign of x becomes positive. And when x is greater than 3, the sign of x is positive. For x minus 3, when x is less than minus 2, the sign of x minus 3 is negative. Between minus 2 and 0, the sign of x is negative. Between 0 and 3, the sign of x is negative. and but when x is greater than 3, the sign of x becomes positive. For x plus 2, when x is less than minus 2, the sign of x is negative. And when x is between minus 2 and 0, the sign of x plus 2 now becomes positive. When x is between 0 and 3, the sign of x plus 2 is positive. Likewise, when x is greater than 3. So we can multiply these signs to know the sign of f of x at these regions. So this becomes positive, this becomes negative, and this is positive. So we know how the values of the function will look like at that point. So using all the information that we have, we can now sketch the curve. It means to the left of minus 2, the function lies below the x-axis. Between minus 2 and 0, the function lies above the x-axis. Between 0 and 3, the function lies below the x-axis. And when x is greater than 3, the function lies above the x-axis. So let's say this is our horizontal axis. And if this is the vertical axis. So labeling the intercepts, we have, let's assume x is equal to 3 is somewhere here. X is equal to 3. This is the origin, which is 0, 0. Then we have x is equal to minus 2, let's say somewhere here. So far, what we know is that the intercept on the y-axis is also 0, 0. So here is where the intercepts on the y-axis lie at this point. The other thing we know is we know the turning points on the curve. We know that x is equal to 1.79, which is a little bit above half of this region. So let's say 1.79 is somewhere here. And that corresponds to a value of minus 8.21 on the curve. So let's try to trace it down here to have an idea of where it will lie. So let's assume at this point, this is minus 8.21. Just a rough sketch. I'm not properly scaling it here. Then at negative 1.12 is a bit above half of the region here. Negative 1.12. Let's assume this is 8.68. So this is 8.68, and we have negative 1.12. So we've set up the turning points on the function, and we've also established the intercepts on the functions. So I think we have everything that we need to solve it. Remember that we said to the left of minus 2, the function is negative. So this means to the left of minus 2, and the lowest value the function can possibly have is infinity. So it just keeps going downward here. So you know that we can draw from minus 2 this way. Then between minus 2 and 0, the function is positive from the behavior that we established. The function is positive. Then it crosses, sorry, my curve is not so good. It touches the y-intercepts and the second x-intercept there. And between 0 and 3, we know that it is negative. So definitely it comes down here. And since this point is a minimum point, there's going to be a turn in here. Then it goes to point 3. Then at point 3, it then keeps going till infinity. Let me redraw this portion of the curve. properly. So this comes down this way. And with this, we've drawn or we've sketched the curve of f of x is equal to x multiplied by x minus 3 multiplied by x plus 2. I hope you guys can now, after watching this video, I hope you'll be able to sketch any other function that might come up in your personal study or even in your assessments or exams. So with this, we've come to the end of this video and also this series on differential calculus. I hope you were able to pick up valuable pieces of information from the series as a whole and this video. Thank you very much for watching this video.